Let's talk about the timing for some of this. So we call that it takes time for single strand breaks to repair. And so if the time between two fractions is too small, then repair might not have occurred. And it would be similar to giving, well, just one high dose. So repair is important for normal tissues, and the time between fractions is dictated by the need to give the tissue time to repair the radiation damage from the previous fraction. The time it takes for normal cells to repair radiation damage is probably between 30 and 1.5 hours, depending upon cell cycles. Clinically, it's been found, again by trial and error over the years, that a time of 6 hours between fractions is required. Any less than that, and we start to see more severe late reactions in the normal tissue. Here's a plot of radiation damage in the kidney as a function of the time between fractions. As the time between fractions increases, the amount of radiation damage decreases. There was no difference in the rate of repair following doses per fraction of 2 or 7 grays. It all just depends on time, and 6 hours is when it plateaus out. When it comes to dose rate, normal tissues repair better than cancer cells, so low dose rates give you more time to repair damage. This is the basis of low dose rate brachytherapy, which we did for 80 years before people started doing high dose rate brachytherapy. The linear quadratic model has two components. There's the linear component due to double strand breaks. Essentially, a single charged particle traverses and breaks both strands of the DNA, typically killing the cell. This is typically caused by high LET radiation. And we'll talk about high LET radiotherapy later. But even with conventional radiotherapy, we radiate the patient with high energy photons, which are low LET, that produce high energy electrons, which are also low LET because they travel further between interactions. But these high energy electrons slow down to lower energy electrons, and low energy electrons are high LET particles. They interact with matter over very small distances. In other words, they give more double strand breaks. So even with low LET conventional photon radiotherapy, there will be a linear part of the model due to the double strand breaks. The second component to the model is the quadratic component that arises due to two separate single strand breaks that occur close enough together and are caused by two separate particles. Combining these two effects in the same model gives the linear quadratic model. Mathematically, we can use the statistics of rare events because the probability that any specific DNA molecule is going to be damaged is very low. In particular, Poisson's statistics gives the following equation for the probability that no double strand breaks will occur, where P is the mean number of hits per target molecule. The average number of hits per target molecule is going to vary linearly with dose for single particle events. Therefore, the surviving fraction of the cells is of the form e to the power of minus alpha d, where alpha is a constant that describes how likely single hit events are to occur. In other words, if we double the dose, then we will double the number of these single particle events, these double strand hits. Recall that these single particle events occur more readily in high LET radiation. The secondary electrons that are produced via the photoelectric effect and Compton scattering, if they are slow enough, are high LET. That's because the LET, the linear energy transfer, is the energy deposited per distance. And these low energy electrons deposit their energy over smaller distances. For two particle events, the probability that one strand of the DNA is going to be damaged is a linear function of dose. Because again, if the dose, if you double the dose of radiation, then you double the probability that one strand is going to be damaged. Similarly, the probability of the second strand being broken is also linearly dependent on dose. However, what is the probability of both strands being broken? Well, this is going to be proportional to dose squared. Just like statistics in school. If there's a 50% chance of tossing a coin and coming up tails, then there's a 25% chance of doing it twice in a row. In other words, the surviving fraction of cells due to two particle events is of this form. You have e to the power of minus beta d squared, where beta now is a single particle, a two particle event. Pulling all this together and combining the probabilities of single particle events with the probability of two particle events involves multiplying these probabilities. Then we take the log of both sides, and the log of the surviving fraction is a simple linear quadratic. Because of the constants used, the single and two particle events are sometimes referred to as alpha type events and beta type events. Here's an example of the survival rate showing both the linear and quadratic contributions and the combined effects of the alpha and beta events. For clinical work, sometimes it's nice not to have two parameters. In 1989, the British Journal of Radiology published a review proposing the term biologically effective dose, or BED. This is based on the linear quadratic cell survival in radiobiology. The biological effective dose can be written by this equation here, where n is the number of fractions and d is the dose in grey. Big D, the total dose, is usually reserved for n times little d. This form is considered more practical as now there is only one unknown parameter characterizing the tissue, alpha divided by beta. Essentially, the parameter alpha over beta represents the dose with its survival rate due to single particle events only and the survival rate due to two particle events only cross over. Here's a look at some values for the alpha-beta ratio. It turns out that for tumours and acutely responding tissues, alpha over beta is somewhere around 10 grays. And for late responding normal tissues, it's somewhere between 2 and 3 grays. However, as we can see from this table, the values can vary by quite a lot. Just putting in numbers into the previous equation gives us this table. For a total applied dose of 60 grays, notice the BED is higher than the total dose. The biologically effective dose combines dose per fraction and the total dose to a given tissue, characterized by a specific alpha over beta ratio, and quantitatively indicates the biological effect of any radiotherapy treatment. However, as you can see, this doesn't directly correspond with survival. Cancer cells should fare worse in radiotherapy. We've spent a lot of time talking about repair. We'll go back and we'll look at the other R's. Recall the R's of radiotherapy are repair, repopulation, reoxygenation, and redistribution. Interestingly, alpha over beta ratio is sometimes referred to as the fifth R, radiosensitivity.